In this video, I'm going to be covering DC circuit analysis with dependent sources. In previous examples, there have been independent voltage sources and current sources, and then some resistor network. And circuit analysis there has been rather simple, but with dependent sources here, there are some extra considerations you need to have when dealing with these sources, especially if you're trying to find a thevenin or Norton equivalent circuit and trying to do analysis like that. A lot of the principles remain the same. There are just some extra techniques you need to use to work around any complications that come with these sources. In this example here, we have a current-controlled current source. So this current 1.5 IX is dependent on the current going through this branch here, through the 6 ohm resistor. But you can also find voltage-controlled current sources, and then the same thing with dependent voltage sources. So here we're going to find the thevenin equivalent circuit as seen from these terminals AB. And we'll learn some techniques here on how to tackle this. Okay, so this is a circuit we're working with. Again, we're trying to find the thevenin equivalent circuit as seen from these terminals AB. Just as a reminder, the thevenin equivalent circuit will have some independent voltage source in series with a resistor, and that resistor will be the thevenin resistance, and then this will be the thevenin voltage. So we're just trying to take this more sophisticated circuit and have a more simplified model, which will allow easier analysis for things like power transfer and whatnot. So the first step is to find the thevenin voltage, which is actually just the open circuit voltage across these terminals. So when the circuit is on, the voltage that is seen from these terminals, that's our thevenin voltage. And if we look closer, that's actually just going to be the voltage across the 8 ohm resistor. So if we can solve for that, we have what we're looking for. Now to find that voltage, you can use any circuit analysis method you'd like here, namely node voltage or mesh current method, which are two methods I've previously discussed. I'm going to elect the mesh current method just because this circuit lends itself well to that with this current source in between two meshes. So the first step for that is just to label each distinct loop that is in the circuit here. We have two, and just assign them arbitrary current variables. And then you would go on and write your KVL equations for each loop, and that will give you a system to solve. But here we can actually see that this is a super mesh, if you will, because we have this independent current source, or not independent, dependent current source in between these two meshes. So we can't really write a KVL, a complete KVL equation for these smaller loops because we have a component with an unknown voltage. So that's not going to be possible there. But what we can do is use this current source in between the two meshes as kind of one of our constraint equations. So we can notice that we've defined I2 as going this way and I1 as going this way, and we have a dependent current source that is equal to this value 1.5 IX. So that can actually be one of our equations. Now if we look closer, we actually can realize that this current dependent current source, it's dependent on this IX variable here, the current going through this 6 ohm resistor. And the way we've defined these variables, that value is actually just equal to I2. So we can substitute that in this equation. And that simplifies things considerably. And then the next equation we're going to write is the KVL for this outer loop, which we can write because we can find the voltages or represent the voltages for each of these components on the outside. So starting with the 12 volt source, 12 volts, and then the voltage across the 10 ohm resistor will be, according to Ohm's law, the current going through it, which is I1 times the resistance, which is 10 ohms. Then this next voltage here, the 6 ohm resistor, is just going to be the current going through that one, which is IX here, or I2. They are equal. So minus 6 I2. And then finally this 8 ohm resistor will just be 8 times the current, which is I2. And KVL says that's equal to 0. Alright, so I'll just clean up the circuit here so things are easier to see. Now again, so we have our two equations here that we've derived, these two here. You can solve the system whichever way you'd like. We have this super mesh constraint here, which if you just distribute I2 and I1 on opposite sides, you'll get each of the mesh currents in terms of each other's, which simplifies things considerably. So you can use this and substitute it in. I won't show that computation here, but you plug it into any calculator and you should get your values. So for the I1 mesh current, that comes out to negative 2/3 amps, and I2 up to 4/3 amps. So now with our mesh current solved, again we were trying to find the open circuit voltage from these terminals. That's our thevenin, and we found that that would just be the voltage across the 8 ohm resistor. And so now that we know the current going through the resistor, I2, we can multiply those together. Just a simple application of Ohm's law, and we can find that voltage. So it's going to turn out to be 3 amps times the resistance, and that comes out to 3 volts. So this is our Thevenin voltage, which will be for our independent voltage source here. The next step will be to find the resistance as seen from those terminals, which are where things get a little bit more complicated. So after finding the Thevenin voltage across these terminals, the next element we need to calculate is the Thevenin resistance, and that will allow us to complete our simplified model here. Now, in other circuits that only have independent voltage and current sources, what you could do to find the equivalent resistance as seen from your terminals would be to deactivate those sources. For the voltage sources, you would short them, and for current sources, you would open the circuit at the terminals there. And then you would be left with some resistor network that, using series and parallel combinations, you could very quickly arrive at your resistance value. But for circuits like these, and this is one of the distinctions, that have dependent current or dependent voltage sources, you can't really deactivate them because they are dependent on other variables in the circuit. So deactivating them you would lose information that way, and your answer would be wrong. So this is where you have to employ some other techniques to find what you're looking for here. In this video I'll cover two. So one of these techniques you can do is, since we have the Thevenin voltage, what you can do if you want to find the R Thevenin, the equivalent resistance seen from those terminals again, is you can short the terminals, and then calculate this kind of short circuit current, which we discussed previously. This is actually the Norton current. So you short those terminals, and then you would just do normal circuit analysis and figure out what that current value is. And then because you have the voltage across those terminals, you can use Ohm's law, V equals IR, and to find that resistance, you just divide your voltage by your current, by your short circuit current. So we have our Thevenin voltage. If we just find the current that results from shorting those terminals, we would get our resistance value. Now, alternatively, and this is a kind of new method here, we can do what's called the test source method, which is where you insert a test source. It can be of arbitrary value, but typically you just do a 1 volt source, so all the computations are easy because you're multiplying and dividing with a unit. And you would deactivate your independent sources. So in this case, your 12 volt source here would be shorted, so you would just be like this. And again, you would do your normal circuit analysis, and you find the current that results from that 1 volt source. You can label it I naught, and similarly, you divide the voltage source by that resultant current, and that would give you your Thevenin resistance. So these are two methods that you can use to calculate that R Thevenin. So we'll use the first method here, which is shorting these two terminals and finding the current that results. From previous examples, this is actually finding the Norton short circuit current when you're trying to construct this equivalent circuit with a independent current source and a resistor in parallel. This is I Norton, what we're finding here. Now, and when we solve the circuit and find what this value is, because we have solved for the Thevenin voltage, which we found to be 32 over 3 volts, if we just use Ohm's law and divide that Thevenin voltage by the Norton current, we'll be left with our Thevenin resistance, which is again the resistance seen from those terminals. So we just need to solve this circuit and find out what this current actually is. I'm going to use node voltage method here just because we have a lot of current variables defined here, and node voltage method lends itself well to that because we're writing KCL equations. So the first step here is to identify our nodes and find our reference node that we're gonna label. So this is actually all a node. Now that we've shorted those terminals, we're effectively disabling this 8 ohm resistor. Essentially no current will be flowing through it because we're shorting those terminals. Again, current takes the path of least resistance. So we can label this as a reference node here. So this will be our 0 volt reference. This is a node, and this 12 volt source will make sure that that's 12 volts. So we don't have to label that as a variable. And then this central node here we can label as V1. It's unknown. And we can write our KCL equations for this. Again, just as a reminder, KCL, Kirchhoff's current law, states that the sum of currents entering a junction is equal to the sum of the currents leaving. So whatever configuration there. It's just a application of conservation of charge. Charge can't be destroyed. So here we're going to start at our unknown node, here V1, and we're going to define the currents as exiting the node. This is just a custom. You can say that they're all entering the node. You can say that 2 are entering, 1 is exiting. It is arbitrary. You'll just get some signs flipping. So we're going to start with this 10 ohm resistor. So the current going through this is the voltage across it divided by its resistance. This is just Ohm's law. So that'll be V1 minus 12 volts divided by 10. That's the resistance, and that's the current going that way. And for the current going down, that's actually defined by this dependent current source here. It's just in the opposite direction, so we'll just add a negative sign. So that'll be minus 1.5 Ix. And then the current going to the right through the 6 ohm resistor it's actually labeled as Ix, just how the circuit was defined previously. So that'll be one equation, and then KCL states that that's equal to 0. So with one equation, we can continue on, and we can actually take note that since we've shorted these terminals and we've defined this entire node as being 0 volts here, here on this side of the 6 ohm resistor will just be 0 volts. And since we have a current defined Ix that's driving kind of this dependent current source here, we can actually use that. Since we know the voltage across it now will just be V1 minus 0, or just V1 divided by its resistance, and that is defined as Ix. So now we have 2 equations, and so we can solve for one of these. So I'll actually go through the computation here. Just combine these terms. Negative 1.5 Ix plus Ix, that'll just be negative 0.5 Ix, and then add it to both sides, so you get 0.5 Ix. Here we can multiply this entire equation by 10, get rid of that denominator here. We'll be left with 5 Ix on this side. So this is a simplified equation, and then we can use this equation here to solve for the rest. So V1 over 6 is Ix, so V1 is equal to 6 Ix, and we can plug this in for our V1 in our second equation. So we'll be left with 6ix minus 12 equals 5ix. Distribute this 12 on the other side. We'll be left with ix equals 12 amps. So this is the value for ix. But if we take a look at the circuit, because we shorted these terminals, ix actually is in, because no current will be flowing through this 8 ohm resistor because we've shorted it. So you can see that this 8 ohm resistor kind of becomes irrelevant, and so this is actually all in series here. So we'll just simplify this up. So now that we know ix is 12 amps, that is actually equal to I Norton. That's our short circuit current. Okay, so now that we've found what our Norton short circuit current is, and we also have our Thevenin voltage from before, we can divide these two out. Again, just a simple application of Ohm's law, and that will give us the equivalent resistance seen from those terminals. So our Thevenin voltage from before is 32/3 volts, and we divide our short circuit current. If you do the calculation there, you'll get your resistance value, 8/9 ohms. And this is our Thevenin. So with that, we now have our completed simplified model here for the circuit's behavior at these terminals AB. So for our second method here, we're actually going to use a new circuit, so we get some variety here. This circuit we can see has a dependent voltage source here, specifically a current dependent voltage source. This 8I is this current here going through the 5 ohm resistor. So instead of using regular circuit techniques, we're actually going to solve this one using source transformations, which is a topic I've covered previously. Again, we're going to try and get our Thevenin equivalent circuit. This time our terminals in question are A, B up here, these kind of the 5 ohm resistor terminals. So the first thing we need to find is that open circuit voltage, this Thevenin voltage here. And so we have to solve the circuit to do that. But instead, we're going to take advantage of source transformation topics. So we can see here that we have this 20 volt source, independent voltage source, in series with this 2 ohm resistor here. And on the right side, we also have a voltage source in series with a resistor. Even though it's a dependent voltage source, we can still use the principles here and simplify that. Now, if we recall, what source transformation basically said is that if you have some independent voltage source in series with a resistor, you can always mimic this kind of terminal behavior and substitute in a independent current source in parallel with the resistor. And you have to do a little bit of manipulation with the values. The resistances stay the same, but you do have to change the value of the voltage and the value of the current source. But here we can take note that we can use these voltage sources here that are in series with their resistors and swap them for a circuit like this to get kind of a resistor in parallel with the current source. So we're actually going to do that. Let's get some space here. So we're going to alter this circuit here just a bit. So this current source here will be in parallel with this resistor, and I'll have the changes we make to the circuit in red, and then we'll keep the original circuit in green here. So this current source, to find the value, if you recall, we just need to divide the resistance value, which is 2 ohms, by the voltage. So that'll be 20 volts over 2 ohms. So this is actually going to end up being a 10 amp source to get the same terminal behavior. Okay, great. The resistance value stays the same, so that just stays at 2 ohms, and then everything before is the same. So that's 20 ohms. This is a 5 ohm. This This is a 10 ohm. And then here for this this dependent voltage source here on the right with a value of 8i, we can use the same principle here. We can just say that it is parallel with the resistor. That's 2 ohms, it's the same resistance value, but this time we'll have a dependent current source. So here, like we changed it to an independent current source because it was an independent voltage source. This time we'll do the same, but they're dependent sources. So again, this dependent current source will be its original value divided by the resistance, this 2 ohm resistor, and that gives us our new value, which is 4 I naught. And if we remember, this is I naught as defined. So we're just using source transformation, and we're changing these voltage sources that are in series with their resistors and giving them an equivalent circuit that is that are current sources in parallel. So now, because we did this, we find that we have these resistors here that are now in series, or now in parallel, that weren't before. You can see here they were, this 10 ohm and this 2 ohm were, it wasn't possible to simplify them in series or parallel. And here, likewise, this 2 ohm and 20 ohm, couldn't do that. But now, using source transformation, they're in parallel, so we can simplify those even further using the parallel resistor formula. Here we'll simplify the circuit even more. This 10 amp source will remain. Here we'll have this new resistor that is the parallel combination of the 2 ohm and the 20 ohm. That's the symbol for parallel. 5 ohm resistor is the same, and here these two, this 10 ohm and this 2 ohm, we can simplify that to one resistor. For the 10 ohm parallel with the 2 ohm. And this dependent current source again remains the same. That stays as 4 I naught, and do not forget how I naught is defined. So we can see that we've simplified from the original circuit considerably. Again, we're trying to find the Thevenin voltage, so that's still these terminals here from the original circuit here. But now we're going to use source transformation again here, because by simplifying these resistors, we can swap back to our original configuration. So kind of this portion here. Just got to identify what we're looking at here. These current sources are both in parallel with a resistor, so we can turn those into a voltage source in series using source transformation. Okay, so starting with this left side of the circuit here, with this 10 amp source in parallel with this 2 ohm and 20 ohm combination, we can again use source transformation and revert it back to a series voltage source and resistor. So in green here, so this voltage source will have a value of 10 amps times the 2 and 20 ohm in parallel combination, and then the resistor will still be that 2 ohm parallel with 20 ohms. Now if you do the calculation, this actually comes out to about 1.82 ohms. And then for this 10 ohm and 2 ohm combination, that comes out to 1.67. But for now I'll just keep them as their unsimplified values. And we can keep that 5 ohm resistor unchanged, as I naught going through it. And then for the right side, with this 4 I naught dependent current source in parallel with this 10 ohm and 2 ohm combination here, we can kind of keep that resistor here, 10 ohm and 2 ohm, and then this dependent current source becomes a dependent voltage source again, with a value of 4I0 times that 10 ohm and 2 ohm parallel combination. So we can see here, just using source transformation, we were able to convert the original circuit with all its individual loops and whatnot into a single series circuit that is, it's rather easy now to solve for the voltage across this 5 ohm resistor. If you remember, we're trying to find this Thevenin voltage. So given that this entire circuit is in series, you can actually just write a very simple KVL and figure out what that I0 is, and then use Ohm's law there. So I'm actually going to move the circuit over here, blow it up a bit. So again, it's one loop, everything's in series. Just write your simple KVL and set those voltage drops equal to 0. Well, I'm not going to show the computation here, but you'll get that I0 is equal to 1.2 amps. And now that we know that current, that's the current going through the 5 ohm resistor, and again we're trying to find this open circuit voltage across the 5 ohm. That's our Thevenin voltage. So if you just multiply that resistance by that current, you'll see that the Thevenin voltage here across this 5 ohm resistor is 6 volts. So now the next step is to find the equivalent resistance from those terminals, and that will give us all the information we need to have our simplified Thevenin model. Okay, so now we got the circuit cleaned up a bit. Now that we found what that VThevenin is, 6 volts, the next step to get that simplified model is to find the equivalent voltage seen, or equivalent resistance seen from these terminals. Now, in previous circuits with only independent sources, you could deactivate those independent sources and then find or simplify the resistor network, and then you'd get your resistance value. But obviously now we have this dependent source where, as previously mentioned, we can't deactivate it. So we're going to have to use another technique to figure out what this resistance is from these terminals AB. So in the last example, we used the example of shorting it, finding this current, and then dividing it by the Thevenin voltage. Here we're going to use a different method called the test source method, where you essentially put a 1 volt independent voltage source in between these terminals, the terminals in question, and then you solve the circuit and find out what the current leaving that source is, and then use Ohm's law to find what the equivalent resistance is. And we use a 1 volt source because it makes computations much easier. Now you still have to deactivate the independent sources here. So, like for example, this 20 volt source would be shorted. So it's only the 1 volt source that we're looking at, and we solve the circuit as normal. We figure out what that IR is, and then we're able to use Ohm's law to figure out what that equivalent resistance is. Okay, so here to save time, I've just rewritten the circuit here. We see by shorting this 20 volt independent source, the 2 ohm and the 20 ohm resistor effectively become in parallel, because by shorting this node here, the bottoms of these two resistors are connected to the same node. So those can be combined in parallel combination using that formula, and that'll give you 40 over 22 ohms, and then we can just copy the rest of the circuit. But this is the circuit we're going to do analysis on and find out what that IR is. Alright, so this is the circuit we're working on. Just as a reminder, I've labeled the terminals AB, which are the terminals in question that we're trying to find the equivalent resistance of. So now that we have this test source here, and we've defined this current IR, we just need to solve the circuit and figure out what these values are, and then we'll be able to find what our equivalent resistance is. So I'm going to use nodal analysis here, and I'm going to pick our reference node here and label this as this node. I'm doing this node because we have this test source here. So if we know that this is 0 volts, then we know that this node will be 1 volt because of this independent voltage source. I'm I'm going to label this bottom node here V1. And then because of this voltage source here, we know that whatever this node is, that'll be V1 plus the value of the voltage source, which is 8 I naught. And then we can begin writing our KCL equations at each of these nodes. So we'll start with this 1 volt node here. So we know the current going up is just IR, it's the same branch, but it's in the opposite direction. So that'll be negative IR. And then we know the current going this way is I naught. And for the current going down, that'll just be our 1 volt source minus the voltage V1 divided by that resistor. Again, this is Ohm's law. You know the voltage across each of the terminals of the resistor and the resistance, we can find the current. And that will be equal to 0. Now for our second equation, we can take a look at this middle node here, our reference node. So again, for the current going up here, it's just IR. So do IR here, and then for the current going to the left, we see it's I naught. They're just in the opposite direction, so that'll just be a sign change. And then for the current going down through this 10 ohm resistor, that'll be the voltage here, which is 0 volts, subtracted by V1. So that'll be negative V1 over 10 ohms. And finally, the last sort of branch here going to the right, we can see that'll be 0 minus this value divided by the resistance. So if we do that, we'll see we get 0 minus that value, so there'd be a negative sign here divided by that resistance. So this is our second equation. We still have 3 variables, so what we can do here is we notice that I naught, since we have defined our reference node 0 volts here on this side of the resistor, and there's a voltage source here, so we know this voltage is 1 volt. We know the voltage on each of the sides, and we know the resistance, so we actually know I naught. So if we look at I naught, that'll actually be equal to 1 minus 0 volts, which is 1, divided by the resistance, which is 5. So that'll be 0.2 amps. Okay, so now that we've obtained these 3 equations, you can use any technique you like to solve them. We have 2 equations and 2 variables now. I'm not going to go through the entire computation. I'm just going kind of through the process of setting up these equations, especially when you have one of these dependent sources present. But you should find that your IR, which is what we were trying to find in the first place, that current coming out of that 1 volt source, or getting produced by that 1 volt source, you'll find that this is equal to 870 milliamps. And again, from the beginning, we said that if we could find this value, we can use Ohm's law and divide those 2 out to find our equivalent resistance from these terminals. If you do that, you should find that your equivalent resistance is about 1.15 ohms. Alright, so I've just brought back the original circuit here now that we've figured out what our values are. So again, we were trying to mimic this circuit's behavior and get a simplified model across these 2 terminals here. So now that we found previously that our Thevenin voltage was 6 volts and that the resistance across these 2 terminals is about 1.15 ohms, we now have all the information we need to simplify this entire circuit's behavior at these terminals. So again, if we have our terminals A, B here, and we know the behavior at these terminals, we can write this simplified model here. So this resistance value is 1.15 ohms like we found, and then this Thevenin voltage is 6 volts. So this circuit will behave exactly the same as this more complex circuit at these 2 terminals.